The story of G6P, or glucose 6-phosphate. We're going to have a lot of these stories, particularly about molecules that we know are branch point metabolites. So we'll frequently just refer to them as BP metabolites. So nice overview here of some things that we've already learned about, some things that we've learned about maybe not in detail, but we've touched on, and then some things particularly to this learning unit that are new. So what I'm going to do is just sort of walk you through this figure, a great figure again to summarize things that we've learned about and to introduce some of the things that are new, particularly as they relate to this branch point metabolite. Remember, branch point metabolites are kind of metabolites that things feed into and out of. So let's first sort of start over here on the left with glucose being converted into glucose 6-phosphate. So right, we know this as part of glycolysis. It's the first step of glycolysis. Remember, we talked about since G6P was an important branch point metabolite, that's why that hexokinase enzyme is not responsible. So this again is hexokinase. That's why even though that enzyme had a large negative delta G value, it wasn't a good flux control point because we knew there was going to be a lot of G6P that could feed in or out of glycolysis. Okay, so a key here, and we haven't really learned about gluconeogenesis in details, but an important part to this process here is the reverse step, taking glucose 6-phosphate, snipping off that phosphate and generating free glucose. The enzyme responsible for that is G6Pase. And why this is really important is only free glucose can be exported and transported in the bloodstream. So only free glucose can be exported from cells, and again, we're going to be using those GLUT transporters. GLUT2, again, transporters are going to allow us to kind of get it in and out of liver, and then GLUT4 we've got in muscle cells, but as we're going to highlight, we're not going to be using that. So GLUT4 is a transporter that we're not going to be using here, but again, only free glucose can be exported and then transported in the bloodstream. So stuff that we've learned about already with glycolysis and hexokinase, but again, the reverse of that hexokinase step uses an enzyme called G6Pase, which is going to be a key player in us understanding the difference between liver and muscle cells. All right, let's go over here on the right and let's talk about the pentose phosphate pathway. So the pentose phosphate pathway, we talked about the two main things that we synthesize in the pentose phosphate pathway that we've discussed are ribose 5-phosphate, that's going to be used for nucleotide synthesis, and then NADPH. So two main things that we talked about that were important with NADPH synthesis, where it was used for lipid biosynthesis and also for glutathione regeneration. Okay, so stuff that we've already sort of talked about along sort of that horizontal piece here. Let's start looking kind of along this central axis here. And this is really the heart sort of metabolism, is where we're thinking about things like glycolysis, right? So glycolysis is actually listed here. So again, glycolysis is listed here, going through its entirety, generating pyruvate, right? We're going to talk about this chemistry here. This is pyruvate dehydrogenase chemistry. It's important to highlight that this is a one-way process. That's going to come into play in something we're going to discuss at the end of this video. And then acetyl-CoA feeds into the citric acid cycle. And at the end of the day, this is really where sort of the important pieces to generate a lot of biological money. ATP happened through the citric acid cycle, and then electron transport and oxidative phosphorylation. So we've sort of learned about this central pathway in kind of a 30,000-foot view, if you will. But now we're going to start mapping on and learning some details. So I'm going to talk all the way at the top here because we have already learned about glycogen. So let's remind ourselves the two places that we see glycogen. We see glycogen primarily in your liver and then skeletal muscle. And we've highlighted this already, but the glycogen stores that are in your liver are intended to be used globally, okay? And in skeletal muscle, that glycogen is intended to be used only for local use. And here's one of the reasons why, tying in something that we've already sort of discussed here. There is no G6Pase in skeletal muscle. So if skeletal muscle, and let's follow the path here, takes its own glycogen and through glycogen breakdown processes makes G6P, because it lacks G6Pase, it cannot generate free glucose that could then be exported. And that's an important safeguard for muscles, which we're going to call kind of selfish, because the glycogen stores that are in muscles are intended for their own use. Okay, so this learning unit here is about these steps. Really, glycogen breakdown, which we can give another name to. We can call this glycogenolysis. Okay, and then we've got glycogen synthesis. So we're going to learn about and think about this again as a substrate cycle, right? So interconverting essentially glycogen and glucose 6-phosphate. And again, this is going to be a need state sort of arm of the pathway where we're breaking this down when we need energy or glucose. And then this is a fed state arm of the pathway. Lots of substrate cycles we're going to learn that kind of highlight that. Okay, let's highlight and touch on some other things that we've already sort of learned about here. We've learned about gluconeogenesis, right? That is sort of the reversal of glycolysis, the interconversion of pyruvate and glucose 6-phosphate or glucose by a large substrate cycle. And that's one of those important mechanisms that we can maintain that 5 millimolar glucose homeostatic sort of situation. We need to maintain glucose at 5 millimolar. But one of the things that we'll see as we sort of go through the rest of this slide here, this is a fairly costly process, right? We actually need to put money in. So we should highlight that this is money in, this is money out here. So it's going to cost energy to sort of do that glucose synthesis. So as we sort of think about the rest of the things that we have here on this slide, I'm going to sort of highlight and use this as a way to discuss how the Atkins, or for that matter, any other carbohydrate restriction diet is sort of going to work. Okay, so one other piece to sort of highlight here that's actually not on this slide is I want to talk about how lipids are sort of metabolized. We've learned the terminology that lipids are broken down in a process called beta oxidation, and that process generates acetyl-CoA. Okay, so acetyl-CoA can then be broken down further in the citric acid cycle and so forth to generate energy. But what we're going to do here is highlight, and those of you who have learned about some details, let's say, of the Atkins diet or carbohydrate restriction diets, is how they are so helpful for people who want to sort of lose weight. And we're going to talk about why it's so easy or easier to lose weight. But I also want to make sure we don't lose sight of the hormonal piece here. But I'm just going to talk a little bit about sort of the energetics here that happens when we consider the Atkins diet. Okay, so some things to sort of think about here is, again, another piece that's not really labeled on here, so I want to just add it in because it's something we're going to talk about, is when we think about amino acid breakdown. Amino acid breakdown basically is going to generate alpha keto acids, and then we're going to deal with that nitrogen atom in the urea cycle. And this is a huge oversimplification of how that happens. But basically, when we've got an amino acid, that nitrogen part gets dealt with in the urea cycle, and then the remaining carbon atoms, or that alpha keto acid skeleton, is going to be used in a lot of different ways. And we are going to have two different kinds of alpha keto acids. We could have ketogenic, and then we can have glucogenic. So highlighting where these amino acids could kind of go back in, right? If we've got ketogenic amino acids, those amino acids resemble acetyl-CoA. So that's where they can enter in this metabolic pathway. And this is sort of the big key here. Because this pyruvate dehydrogenase chemistry is irreversible, once you've gotten to acetyl-CoA, you cannot go back into glucose. So this is a really important piece to highlight, that because ketogenic amino acids can only be made into acetyl-CoA, that also ensures that ketogenic acids amino acids cannot be made into glucose. So ketogenic amino acids cannot be made into glucose. And we've talked about this before, but just to highlight again, this also means that lipids, because they are converted into acetyl-CoA, so fats cannot be made into glucose. Well, if you've sort of learned about some aspects of what the ketogenic diet or Atkins diet or a carbohydrate restriction diet sort of involves, it's largely the consumption of proteins, which again are going to generate amino acids, and then lipids, carbohydrate restriction. Now, remember, even though we're doing carbohydrate restriction, it's really important that we have sugar around, that we have glucose in our bloodstream. So gluconeogenesis is going to be what manages that. But the key is that we are going to be using only glucogenic amino acids to sort of satisfy that synthetic pathway. Okay, so Atkins diet is going to require protein. Specifically, it's going to require glucogenic amino acids because those glucogenic amino acids are going to be made into pyruvate. Should have kind of highlighted this arrow here. Glucogenic amino acids can be made into pyruvate. And once we've done that, then we can have gluconeogenesis, synthesize the glucose that we need to maintain that 5 millimolar kind of blood sugar level. Okay, highlighting that this is not a process without energetic cost. Let me change colors here. Okay, we need to put some energy in. So where does that energy come from? Well, that energy is actually going to come from lipids. Okay, so highlighting the things that we need to sort of consume in this carbohydrate restricted diet. You need to have protein, specifically glucogenic amino acids, because you need to have the ability to maintain 5 millimolar blood sugar, but that's a costly process. So you can consume lipids, or why this diet works to lose so much weight is these lipids are your own internal reserves. Beta oxidation generates acetyl-CoA. We're going to break those down, and this money then is used to sort of fund that process, if you will. So highlighting that this money out, so lipids are going to generate that money out. A lot of arrows here, I know. And that money out is going to fuel that process for synthesizing glucose. Wow, a lot here, but again, it's important to understand how carbohydrate restriction diets work. This is largely looking at it from sort of the energy expenditure sort of standpoint. But remember, one of the other key features that happens when you do carbohydrate restriction is you blunt your insulin response. So you're going to have significantly lowered insulin levels, and that's going to allow you to better tap into your own stores of lipids to be able to generate the energy to synthesize the glucose that you need from those glucogenic amino acids. Wow, that was a lot there. But glucose 6-phosphate, G6P, really critical branch point metabolite for lots of different metabolic processes.